Here we're in Module 12. We're looking at an introduction to probability distributions. So in our previous discussions of probability, we focused more on determining the probability of one outcome at a time, such as estimating the probability of a head and a toss of a weighted coin. Now we shift to focus on describing the probabilities of all possible outcomes instead of the probability of just one outcome. Statisticians describe outcomes as variable values. Each variable value has a probability. All possible variable values together with their probabilities are a probability distribution. So for example, let's look at the probability distribution for a fair coin toss. The variable is coin toss. This is a categorical variable with variable values, heads, tails. The probability distribution assigns each variable a value, H or T. Each one is going to have a probability. In this case, we use theoretical probabilities to create the probability distribution shown in the table. So here's our table. The coin toss outcome would be either heads or tails. The probability of each, since it's supposed to be a fair coin, is 0.5 for each. Now we'll look at the probability distribution for a weighted coin toss. The variable is still a coin toss. This is a categorical variable with variable values, heads or tails. The probability distribution assigns each variable, H or T, a probability. In this case, we have to estimate the probability of each outcome, H or T, using relative frequencies based on a large number of coin flips. In the table, we use empirical probability estimates to create a probability distribution. So we're going to assume that the probability of heads is 0.201 because it's a weighted coin. And this is empirical probability, so it's not theoretical. This has actually been maybe done in an applet, or someone's actually flipped this coin 1,000 times. But if the probability of heads is 201 out of 1,000, the probability of tails must be, well, there were 1,000 coin flips, 201 of them were heads, the rest must be tails. How many are left? 799 out of the total number of coin flips, 1,000. And those divide out to become 0.799. And now we'll look at the probability distribution for blood type. This is a little more complicated because there are more variables. You're not just going to have heads or tails. There are more than 2 blood types. So it'll be a little more complicated. Let's consider the variable blood type. This is a categorical variable with variable values A, B, that's just one item, right? or O. Using empirical probability estimates, which are relative frequencies from large samples of randomly chosen individuals, we can estimate the probability of choosing a person with a given blood type. Using relative frequencies, the Stanford University's Blood Center gives the probabilities of human blood types in the United States as follows. So maybe I'll zoom in on that. Let's see. We can see it better now. Okay, the probability of having an O blood type is 0.45. So it's almost half. Half the people have have O blood type. Quite a few have blood type A as well, 0.41, pretty close to half. B blood type is more rare, 0.1, so that's 10 out of 100 or 1 out of every 10 people. Then AB blood type is the rarest, it's 0.04, that's 4 out of 100 people will have that blood type. Okay, so I never remember what blood type I am, I just remember that I'm the most common, so now I remember it's O, that's right. Thanks for reminding me. Okay, we can use the probability distribution to answer probability questions. For one question, we can say, well, people with blood type O can donate blood to people with any other blood type. For this reason, people with blood type O are called universal donors. What is the probability that a randomly selected person from the United States is a universal donor? The answer, probability of universal donor is the same as the probability of blood type O, because those are equivalent, which is 0.45, which I see in the table here. There's a 45% chance that a randomly selected person in the United States is a universal donor. Now here's another example. Probability distribution for boreal owl eggs. Boreal owls are common in Canada and Alaska. They are fairly small, averaging 10 inches in length and weighing from 4 to 6 ounces. They often make their nests in woodpecker holes. Using relative frequencies from large field observations, we can estimate the probability of a nest containing a certain number of eggs. The variable is boreal owl eggs in a nest. This is a quantitative variable with values 0, 1, 2, 3, 4, 5, or 6 eggs. I guess they've looked into it and they haven't seen a nest with more than 6 eggs. That's why they stopped at 6. The probability distribution gives the probability that a nest will have from 0 to 6 eggs. Okay, so it looks like the probability of having 0 eggs in a nest is 0.2, so 2 out of every 10 times you'll see no eggs in a nest. The probability of 1 egg is 0.1, probability of 2 eggs is 0.1, probability of 3 eggs 0.25, probability of 4 eggs 0.25, probability of 5 eggs is 0.05, more rare than all the other values so far. 6 eggs is the same, 0.05. So 5 out of 100, every 5 out of 100 times you look in a boreal owl nest, you'll see 5 eggs, and then same for 6. This table is also another example of a probability distribution, because basically this shows the probability of all outcomes all at once. There have only been 0 through 6 eggs in a nest. This shows the probability of all of them. So they call it a distribution because it kind of covers all the possibilities, I guess. Each variable value is assigned a probability. For example, we can answer the following question from the probability distribution. If someone were to ask, okay, which is more likely, either to find a boreal owl nest with 3 eggs or to find a boreal owl nest with 4 eggs? We just go up and look here. Okay, they're comparing 3 eggs to 4 eggs. Well, we see the probability of 3 eggs is 0.25. The probability of 4 eggs is 0.25, so they're the same probability. To answer, both of these events are equally likely because the probability of 3 eggs is equal to the probability of 4 eggs. They're both 0.25. You have a 25% chance of seeing 3 eggs, and you have a 25% chance of seeing 4 eggs. So they're equally likely. Now notice the following important facts about probability distributions as we've seen in the examples above. First, all outcomes are assigned a probability. Also, the probabilities are numbered between 0 and 1. We've seen that before, that probabilities should always be between 0 and 1, some kind of decimal number. This makes sense because each probability is a relative frequency. It's the number of times an outcome occurs out of the total number of observations. The third thing we can notice is the sum of all the probabilities is 1. If you look at any of the tables above, any of those probability distributions, you'll see that all the values in the probability boxes add up to 1. This makes sense because we have listed all the outcomes. Each probability is a relative frequency, and the relative frequencies will add to 1.